All right. So what we had started last time, or actually, let me just go over this briefly. So we went over the steps to calculate the element stiffness matrix and the element force vector for a general Q4 element last time. Um, so the idea is that if somebody gives you the 4 coordinates of a general Q4 element, you should be able to calculate all the different quantities in there. But the first step is we map a general Q4 element back to its parent element. We generate the shape functions over the parent element, which we know are just one-dimensional functions, which are products of xi and eta. We also calculate the derivatives of those shape functions. Now these derivatives are with respect to the parent coordinates. But these derivatives are not the ones that go into the B matrix. So to calculate the derivatives that go into the B matrix, we have to calculate the Jacobian first. And for calculating Jacobian, we have to calculate each of those terms using these expansions. So once you calculate the Jacobian, you can calculate its determinant and its inverse. And this is all at each Gauss point. At each and every Gauss point, you have to do this. And finally, you can calculate the derivatives with respect to the actual coordinates, which are x and y. Once you have this, you can construct your N matrix, which remains the same for whether it's parent coordinates or actual coordinates. Then you construct your B matrix. And finally, you can just add your contribution from the current Gauss point to your element stiffness matrix, add the current contribution to the element force vector, and then if there are edge loads on the element, then you have to repeat this process for each of the Gauss points at each of the edges. So basically, once you are finished with all these 3 or 4 steps, and each of these, the steps 2 and 3 require further sub-steps for each and every Gauss point. Once you are done, then you would have your K element. You can go and assemble that into the global stiffness matrix and enforce your boundary conditions, solve for it, and so on. Okay, so that's basically the outline of how you would implement it on a computer. And then last time we also started to take a look at some of these higher order elements, and especially for the triangular element. So what we said was that if somebody gives us these coordinates 1, 2, 3 of a triangle, we know how to calculate the shape functions for a T3 element. But let's say now, and we also saw that that T3 element was complete up to the linear terms. This is the constant strain triangle T3. So since it is complete up to linear terms, what is the order of convergence that is going to be in displacements? Quadratic. So if it is linear, then the order of convergence in displacements is quadratic. Order of convergence in stresses is linear, p and p plus 1. Similarly, we can construct higher order elements. So in this case, you have a T6 element, which is also called the linear strain triangle. What that means is that we are approximating displacement within this triangle as a quadratic function. So this T6 element is going to be able to approximate all the quadratic terms, and therefore its convergence order in displacement will be cubic. Since it is complete up to order 2, so p is equal to 2, therefore p plus 1 is 3. Therefore, for the errors in the displacement, it is going to be cubic in the errors in displacement. Similarly, you have all these higher order elements where you can just keep on adding nodes on the sides. And the idea is that in this case, you add a mid-side, this node on the middle of this edge. In this case, you are adding nodes at the 1/3 of this edge. And the way that I have drawn these red, blue, and green lines, they should tell you that there is some structure to this kind of a node enrichment within this triangle. So you can keep on adding this, and the good thing about this triangle is that all the terms up to a certain order can be completed by just adding more and more nodes to your triangle. So so the next thing is now that let's say we have these coordinates of these 3 points, and we want to use some triangle, let's say T10. So the first thing that we need to do is to generate the shape functions and the shape function derivatives for any general triangle with multiple nodes. Okay, and to generate the shape functions, what we also said last time was that we will use what are called area coordinates. So the idea is that given these 3 corner nodes, uh, any interior point x, y. So these are the 3 corner nodes. If somebody gives us this interior point, we have to be able to express the value of that interior point in terms of its nodal coordinates. So the idea is that we will construct these 3 triangles that go from this interior point to all these vertices, and the triangle, this red triangle right here, that is going to be um, the area of that red triangle divided by the total area is L1. That's the area coordinate. That's, we are just creating something, we are just changing a variable. Okay. So similarly, you have L2, which is this area, green over the total triangle and blue over the total triangle. And obviously, since the sum of these 3 triangles is going to be equal to delta, which is the total triangle, therefore, if you add all these 3 up, you should get 1. You should get delta divided by delta, right? So these are these area coordinates, which are not independent, because obviously they should not be. We have only 2 independent coordinates, x and y. So we cannot create a third independent coordinate out of thin air. This is the relationship that relates the 3 area coordinates. So in effect, we still have 2 independent variables. Now that we have created these area coordinates, we'll see how to construct the Lagrange shape functions for a triangle. And this is fairly neat and maybe a little bit tricky too, so try to follow this. So just to recap a little bit, this is the description of how we created Lagrange shape functions for one dimension. If you remember, for the 3-noded linear element, how did we construct our shape functions? Let's say we had 3 nodes. We said that the first shape function is this, the second shape function was this, and the third shape function was this. So the same idea can be generalized to any number of nodes. And this is a property of Lagrange polynomials that you can create those by just adding factors at different points. So let's say you have n different points. You want to calculate the Lagrange function for the point k, that is that this function goes to 1 at point k and goes to 0 at every other point. Okay. So the way to construct that Lagrange function is you start multiplying factors. So this is C0, and let's say this is a function of C. So C minus C0 immediately means that whatever function we are constructing will go to 0 at 0. C minus C1, that means it goes to 0 at 1. C minus C2, that means it goes to 0 at 2. The term C minus CK, that is missing in here. So it will not go to 0 at k. In fact, it will go to 1, because in the denominator we are going to multiply the exact same terms that we had in the numerator, but except we'll substitute the value ck for c. So if you take a look at this function will go to 0 at all the points except ck, and when you substitute c is equal to ck, this numerator and denominator are exactly same, and this will cancel out to give you 1. Okay, so this is how we construct Lagrange functions in one dimension. And this is just a bit of a notation here. This notation pi, this capital pi, this is something similar to sigma, the summation symbol that we use. This just means that we are, instead of summing up these terms, we are multiplying these terms, which means we take this term, multiply with this term, multiply with this term, and so on. So this is just a shorthand notation for this expanded formula. Okay. So now that we know what are the Lagrange functions in one dimension, we are going to utilize these Lagrange functions to actually come up with what are the shape functions for a general triangle. And the idea is that, let's say we have this triangle, and there are all these multiple nodes inside this triangle, where we are saying that, so we are saying that in each direction, let's say L1 is going like this, which means that L1 starts from this edge, and it goes all the way up to here. So for any point along this edge, L1 would be 0, right? And as you go up here to reach the point 1, L1 reaches 1. So this is L1 starts at 0, goes all the way up to 1. And we are saying that we will construct a Lagrange shape function for this point, which is denoted with I, J, K. These are the triangular indices, if you will. So the indices in this case will start from 0. So here is 0, 1, 2, 3, 4, 5, 6. In this case, we have six indices or 6 nodes in each of the L1, L2, L3 directions. And what we are saying is that this node can be represented as a combination of these indices. So we have 0, 1, and 2, means I is equal to 2. Similarly, for the L2 direction, which is this one, let me see if we can zoom here a little bit. So L2 goes from 0 to 1 in this direction, which is anywhere along this edge. L2 is 0, and as you reach the node 2, it will reach, the value of L2 will reach 1. And it starts at 0, and it goes up to 1, which means J is equal to 1. So this is just a notation we are using to denote the location of any node inside the triangle. Is that notation clear? No? Okay. Okay, let's go over this again. So we just said that there are 6 nodes in each direction. Okay. If you go from this edge all the way up to here, you are traversing 6 lines. So this is 0, 1, 2, 3, 4, 5, 6. And the same thing is valid for 2, and the same thing is valid for 3. And you should relate this picture to this diagram also. If I start here, the area of triangle L1 is 0. That's why L1 is 0 everywhere along this edge. If I move up 1 point, then the L1 triangle will be something like this. So L1 is small, but so as we keep on going from this edge all the way to this edge, the area of L1 keeps on increasing, the area of L2 and L3 keeps on decreasing. Okay, so in general, for any node inside the triangle or on any of these edges, we can denote the location of that node by 3 indices I, J, K, which are just the location of L1, L2, and L3. So in this case, we start from 0 and we go up to 1 and 2. So I becomes 2. For L2, we start from 0 and go 1, therefore J becomes 1. For K, we are going to go in this direction, therefore we start from 0, 1, 2, and 3. So K is 3. And if you sum all of these up, I plus J plus K will always turn out to be the total number of the number of nodes in any direction. That is, I plus J plus K will be equal to M. So let's take a look at this. This node is being denoted as M, 0, 0. Why is that? Because if you start from 0 here on the edge 2, 3, L1 is 0. So you go up 1, 2, 3, 4, 5, 6. M is 6. Therefore, this node will be denoted with the indices 6, 0, 0. Similarly, this node, you start from this edge, you go up 1, 2, 3, 4, 5, 6. So this is 0, 6, 0. This is just a notation that we are using because we are going to generate the shape functions in these notations. So similarly, you go up in this L2 direction and this L3 direction, you will see that this is 0, 0, 6. So to generate the shape function for this node alpha, which is I, j, k, what we need is some shape function that goes to 1 at this point and goes to 0 at every other node. So there are all these different nodes. Whatever shape function we generate must go to 1 at this point, and it must go to 0 at every other point. And in order to do that, we are going to use these Lagrange shape functions in the three L1, L2, L3 directions. And the idea is that let's take a look at L1 first. So this is the formula that gives us the shape function for this node alpha. And the idea is that in the L1 direction, we are going to use a Lagrange shape function that corresponds to this index I. So for example, in this case, index I is 0, 1, 2. I is equal to 2. So if you take a look at this point, this is 0, 1, and 2. And the Lagrange shape function for this point is this. This shape function goes to 1 at this point and 0 at both these points. Okay. So since this function goes to 1 at this point and 0 at these points, we don't care about all these points. We are just going to go up to I or up to j or up to k. And which means that any function that you construct in this manner, this is Lagrange shape function in L1 multiplied with this Lagrange shape function in L2 multiplied with Lagrange shape function in L3, which means that this function is going to go to 0 at all of these nodes, right? Because all these nodes correspond to this point. All these nodes correspond to this point. Since this L1 of L goes to 0 at both of those points, all of these nodes, this shape function will go to 0 at all of these nodes. So now we'll repeat the same idea for L2. In L2, you see that you start from 0, go up 1, and the shape function is right here. So this function L1, 1 of L2, that's just a linear shape function that goes to 0 at this point and 1 at this point. So if you multiply this shape function with this shape function in L1 and L2, this will ensure that this point corresponds to all these points. Therefore, this function will go to 0 at all these points now, which means that this shape function goes to 0 at all these points and all these points. So all we are doing is we are multiplying something that goes to 1 at this node and 0 at every other node. And we will construct this shape function so that finally we will have a shape function that goes to 1 at this point and 0 at every other. So in the three direction, you will see that it starts from 0 at this point, which corresponds to this row, and as we go up to the point 3, the value of L3 will go from 0 to 1. Okay. And finally, if you have this this Lagrange shape function that goes to 0 at these line of nodes, this line of nodes, this line of nodes, and goes to 1 at this point, which means that all these nodes will also, this shape function will go to 0 at all these nodes. So finally, if you multiply all these Lagrange shape functions out, you will get a function that goes to 1 here and 0 at every other node. And that's how you will construct shape functions that are in terms of L1, L2, L3 that go to 1 wherever you want and go to 0 everywhere else. Okay. And we'll do a little in-class exercise today based on this, so you'll get some practice about this. One thing to note here is this thing. We are saying that for each of these corner nodes, at least L1, L2, or L3 is going to be 0. So the Lagrange shape function for one of the corner nodes is just defined to be 1. Okay? And let's take an example that might make it a little more clear. So in this case, this is our favorite T3 triangle. And let's take a look how to construct the shape functions. We already know what the shape functions are for this. But let's see if whatever we have just described is consistent with the T3 triangle that we had. So starting from this edge, if you go up in this direction to node 1, the value of L1 will increase from this point or from anywhere along this edge all the way up to this point. It will go from 0 to 1. This is 0 to 1. So this is L1 increasing from 0 to 1. We know that the Lagrange shape function that goes to 0 here and 1 here is nothing but a linear function, right? So the Lagrange shape function is linear, that goes from 0 to 1. So therefore, this function is nothing but L1. Now the other two shape functions, they are L of 0, comma 0. So this is so this is L of 0, comma 0 in the L3 direction, and this is L of 0, comma 0 in the L2 direction. So both of those we have just defined to be 1. So immediately we get that the shape function for this node 1 is this multiplied with this multiplied with this, which is L1 times 1 times 1. The same sort of idea holds for node 2, but you would have to draw a different figure where you have a Lagrange shape function that is linear in L2, and it would be 1 and 1 in L1 and L3. So that would be L2 times 1 times 1, again L2, and similarly for L3. So the procedure that we just described for Lagrange shape functions is consistent for this 3-noded triangle. And this is a little bit tricky, so you have to work with this idea a little bit to make sure you understand this. Now for the more interesting case, the T6. This is a T6 triangle which has these nodes 1, 2, 3, and the mid-side nodes are 4, 5, and 6. Okay, so let's say we want to calculate this shape function for point 1. So in L1, we need to calculate a shape function that goes to 1 at this point and goes to 0 at both of these 2 points. Right? L1 starts from here, goes up to here, which means starts from 0, half, and 1. So what would be the Lagrange shape function for this? For this curve? We have it right here. If you have L1 minus half, that means that this function will go to 0 at half. You have L1 minus 0, means this function will go to 0 at 0. And divided by the same quantity, but L1 is equal to 1, therefore this entire thing is the representation of this curve. This is the Lagrange function, Lagrange polynomial for this curve. Okay, and you take that curve and you multiply it with 1 in the L3 direction, 1 in the L2 direction, and those are 1 and 1, and that gives us immediately the formula for the triangular shape function for node 1. Okay, and if you simplify this, you will see that this is half, this is 1, so half goes up, and this simplifies to this one. Twice L1 minus 1 and times L1. So the other two shape functions are just the same thing in the L2 and the L3 direction. So what we have now is shape functions for the corner nodes, which are 1, 2, and 3. So the in-class exercise that we'll take for the next maybe 2 or 3 minutes is that you need to write what is this shape function for this node 4? And I've already drawn the Lagrange shape function for you. This is a linear function that goes to 0 at 0 and 1 at the midpoint. So you can write out what is the function in L1, the same function in L2, and 1 in L3, and what does it come out to be. So let's take a couple of minutes, and then whenever you're done, don't need to come up. Just hold it with you. Towards the end of the class, you can bring it in. And if you have any questions, you can go ahead and ask. So let's take another minute, and then maybe we'll just turn it in. N4. Yeah. So all you need to do is to multiply this function with this function and this function. This function is already 1. And you can take a hint from this formula. This is the formula for the Lagrange function in L1, which is a quadratic here, but it will be linear in L1 and L2. And the L2 direction is 1, L3 direction is 1. So that's why we have this Lagrange function in L1, quadratic, times 1 times 1. Okay. So yeah, whatever you have done, you can just, instead of coming up, maybe you can just pass it down this row. Yes, that's an N4. All right, so let's take a look at how we would do this. So what is the shape function in L1? It needs to go to 0 when L1 is 0. So the straight away the term that I need to multiply is this, divided by, it goes to 1 at half, right? So half minus 1. And similarly, in the L2 direction, we have the exact same function, but of L2. Half minus 1, or minus 0, sorry. Minus 0 and half minus 0. And in the L3 direction, it's 1. Therefore, what is N4? N4 would be 4 times L1, L2, right? Similarly, N5 would be 4 times L2 times L3. And N6 would be 4 times L3 times L1. And this is a general procedure that you can use to calculate the shape functions for any number of nodes that are in there in the triangle. As long as they are equally spaced, you can show that the sum of these shape functions will be actually 1. Okay, so this is how you would construct the shape functions for the triangle. And these shape functions, as you can see, they are in terms of L1, L2, L3, which we can calculate if somebody gives us the corner nodes. If somebody gives us the corner nodes, and we can immediately calculate what is the value of L1, L2, L3 for any point inside the triangle. And once you calculate the value of that point x, y in terms of L1, L2, L3, we also know what are the shape functions, the values of the shape functions at that point. So, and this is the following relationship. So once we know the shape functions, we need to calculate its derivatives. We need to plug that into our weak form. So in order to plug that into the weak form, we also have to calculate these derivatives, and some of these identities are actually helpful when you are dealing with that. So we already have seen that the sum of the shape of some of these L1, L2, L3 is 1, which comes away straight from the area. There are these two relationships that are nothing but the isoparametric map, meaning any point in this actual triangle xy can be mapped to the L1, L2, L3 coordinates using an isoparametric map. And if you replace this L1 with N1, that's the shape function for this. N1 is equal to L1. N2, the shape function for node 2, that is simply equal to L2. Shape function for node 3, that is simply equal to L3. If you replace N1 times X1, N2 times X2, N3 times X3 with L, you will get this relationship. That's the isoparametric map relationship that we had before. And similarly for the Y direction. How do we calculate this L1, L2, L3? We have seen this before. The shape function for a triangular element we can calculate like this. N1 was those coefficients A, B, and C divided by 2 delta. And that is exactly L1 in terms of X and Y. So what that means is, if somebody gives us these 3 coordinates and the coordinate of some point, x, y, we can calculate what is the value of L1 at that point using this, L2 and L3. Okay. So for the derivatives, what we need, the derivatives that go into the B matrix are derivatives of the shape functions with respect to x and with respect to y. And to calculate that, all you have to do is to take the derivative of this. If you take the derivative with respect to x, you get b1 times b1 upon 2 delta, which is right here. And for y, you have c1 upon 2 delta, which is right here. So similarly, you can calculate the shape functions L2 and L3 and their derivatives with respect to x and y. Okay. All right. So a couple more things about this. We've already seen how to calculate the shape functions, and these are Lagrange shape functions in each of those three in each of those three triangular coordinates. So what is the polynomial order of this Li? So let's consider this one. This I goes from 0, 1, 2, which is 0, 1, and 2. I is equal to 2. So what is the polynomial order of this curve? Quadratic. So this is polynomial order quadratic 2, and in general, if it is I, then it would be, let me not put it as 2I. In general, it will be I. Okay. How about the polynomial order of J? So in J, you are going in this direction. So 0, 1. It's a linear, right? So that means its polynomial order is 1 in this case, and in general, it will be J. And similarly, for the K direction, you have 0, 1, 2, 3, which means that this will be a cubic. And since this is a cubic, you will have 3 here, and in general, it will be of order K, which means that the total polynomial order will be M. The total polynomial order in L1, L2, L3 of this shape function for node alpha is going to be M. And not just for alpha, alpha can be anything. For any node in this triangle, the total polynomial order is going to be M, which is 6 in this case. Okay. So this fact will help us later when we are trying to calculate derivatives and how to calculate the integrals of those polynomials. So to calculate the derivatives, what we need is this derivative of the shape function with respect to x, derivative of the shape function with respect to y, and all that we need to do is to apply the chain rule to this equation right here. These are all in terms of L1, L2, L3. So we'll take the derivative of that n alpha with respect to L1 and dL1 over dx. What is this? This is b1 over 2 delta. This is something that we just did on the previous page, right? This is a constant, this is a constant, this is a constant. So all that you need to do is calculate the explicit expression for this shape function and just calculate this out. So this is something that you can explicitly code up in MATLAB. And similarly for the y direction, and you can and there's a caveat here that in general this is valid only for triangles with straight edges. If the triangle is curved, a lot of the good properties about these triangular elements go away, but then you would have to use an isoparametric map and all that. But all this is valid for a triangle with straight edges. So finally, once you have your shape functions and the derivatives, all that you need to do is to plug them into your B matrix and N matrix, and you will have to calculate these integrals. And we've seen how to calculate these integrals for the constant strain triangle, and we saw that all this was constant. You could take this out and multiply it with the area, and you get your element stiffness matrix. Something very similar happens even for triangles in higher order. In higher order, what we have is a couple of exact formulas. And again, these are valid only for triangles with straight edges. But let's say you have a polynomial which is of order I in L1, of J in L2, and K in L3. This is a product of polynomials in L1, L2, L3. So if you go back to this if you go back to this equation right here, this will be a polynomial in L1, L2, L3. You multiply that out, you will get a polynomial, a big polynomial with where each of the terms would be something like this. So to calculate the total integral, this is an exact formula where this is factorial, I factorial, j factorial, k factorial over all this times 2 delta. Delta is the area of the triangle. And similarly, if you want to calculate the boundary terms, these boundary terms, for one edge, they have L1 times L2 to the power I and j. They can be calculated using this formula. So for any higher order triangle, you can actually integrate the weak form exactly. And that will help you to preserve the order of convergence. So one small note about general triangles. In general, if your triangle has curved edges, you cannot integrate the weak form exactly. And you would have to use something very similar to your isoparametric map that you did for Q4. You have this element. You will map it to this one, and the idea is that L1, L2, L3 will be mapped to. So L1 will be mapped to R, L2 will be mapped to S, and T, which is a dependent variable, is nothing but R plus S plus T is 1. So this gives you the third variable. So R is something similar to your C variable, S is something similar to your eta variable, and there are rules for integration of over a triangular domain, and there are I think we are not going to use that in the code or in the homework problems, but if you want to take a look at how it is done, then there are some details in these two sections in the books. So this is basically how you would do triangular elements of higher order. And the benefit of the higher order is, as you might have seen in your homework 5, if you take a look at the coarsest mesh, the 10 element mesh, it doesn't give you much displacement when you apply the load. And that phenomenon is also called locking. It locks in bending, so all these triangular elements are not good for bending problems. But if you use a higher order triangle, especially a quadratic triangle, the exact solution belongs to that space, and therefore it will immediately give you a much more accurate solution, even with 10 elements, where each of the element is a T6. Okay. So so that's why we use higher order elements. Okay. So moving on to higher order rectangular elements, and in general, there are actually these rectangular elements are much more simple to implement and to work with than the triangular elements. So the idea is, in this case, for the rectangular elements, you have two types of higher order elements. One is called a Lagrange family. One is called a serendipity family. And the Lagrange family is a very simple kind of a shape function family. So the way that we construct this is exactly the way that we did before for Q4. If you have Q4, you can take your linear shape function in C and in eta, you multiply them out, you will have the shape functions for this. Similarly, if you have a Q9 where there are 9 total nodes, you take your quadratic shape functions in C, multiply them with quadratic shape functions in eta, and you will have all the shape functions here. And you can explicitly calculate the derivatives of all these with respect to C and eta. The idea is that this is a parent element. This will be actually mapped to an actual element in the mesh. So similarly, you have Q16, which is a cubic in C, cubic in eta, and this will be mapped to something in the real mesh. So here's the question. How many bubble shape functions are there in this element? 1. So 1 bubble shape function, because at this node there is the function that goes to this function will go to 1 here, 0 everywhere else. So there is this one bubble shape function. How about this? All the interior 4 nodes have shape functions that go to 1 at that node and go to 0 everywhere else. All the nodes that are at the edges, are they bubble functions? They're not bubble shape functions, because if you consider this element as a part of a mesh, then on that edge, the value of this shape function will go to 1, which means that it is sort of connected to the next element, right? Because wherever the value of the shape function goes to 1, it is going to be connected to the adjacent element. So all these interior functions, which are bubble functions, can be statically condensed out, right? And that will reduce the cost of computation. So, but in general, the idea is that all these Lagrange family of shape functions, the types of polynomials that they can approximate, is like this. So for Q4, you have a linear shape function in Xi, linear shape function in eta. You can calculate and you can approximate terms up to, I'm using x and y, but you should in general interpret this as Xi and eta. You can approximate all the way up to xy, or Xi eta, product of Xi eta. So what is the order of polynomial that Q4 approximates completely, quote unquote? To what order of polynomial is Q4 complete? It is complete up to this point, right? The only extra term right here was this, which means it is complete up to linear terms. So when we use Q4, we don't actually get some an extra order of convergence, because it is not complete in the quadratic terms. So the order of convergence in displacement for Q4 and the triangle is going to be the same. Similarly for Q9, you have quadratic in Xi, quadratic in eta, and all the product terms also come in. So you have all this way up to here. But Q9 is complete up to the quadratic term x, xy, x and y square. It is not complete in this cubic term. It is not complete in this quartic term. So the order of convergence will be the same as a quadratic polynomial, meaning displacements will be of the order of h to the power 3, and stresses will be of the order of h to the power 2. All right, so maybe we should stop here, and we'll take a look at this serendipity family next time.